Hello everyone, welcome back. In this video, we'll be discussing about the last problem of today's weekly contest, minimum reverse operations. The problem states that you are given an integer n and an integer p, and you will be representing an array of length n, where each position is set to 0 except the position p. Right? So you will be building an array of length n, everything is 0 except position p, which is 1. Now you are also given an array band, which means that any position in band or any element in band, that position of the array should be 0 and can never be 1, right? So that position of the array is banned to be 1. Now you can perform multiple operations. The operation is you will choose a subarray of size k and reverse the subarray, right? So you are given a integer k and you will choose a subarray of that size and reverse that subarray. Now, as we have discussed, this band positions will never contain 1. That would always be 0. So, because you are reversing an array, it may happen that band position may end up having 1. If that's the case, you can't perform that particular reverse, right? So, some of the reversal are blocked with this band array, right? Now, after this, you will just return a array answer where each index I would denote the minimum number of reverse operation needed to bring one to position I in the array, right? So let's just take an example to understand this entire thing. So let's say this is the problem. We have n equals to 4, p is 0. What does this mean? It means that we have an element, we have 4 elements in the array, each are 0 except p equals to 0, right? So this is the array that we would be forming, right? Now after this, uh, we know there are two band positions. So this is band position, this is band position. So here never, we can't have one here at all. Now k is 4, it means we can reverse a subarray of size 4, right? So let's try this. So we can reverse a subarray of size 4. How many subarrays of size 4 are there? Only one, right? So you can do, like, can you reverse this subarray of size 4? Answer is yes, you can reverse it, because after reversal, the array would become 0, 0, 0, 1, right? And you can see any of the band position doesn't contain 1 after this operation. So this is valid reversal. And you can see after reversal, the fourth index have 1. So basically what we are saying is we have to prepare the answer array, right? Where each index would denote what is the minimum reversal operation required to make that 1. So in the value of index 0 would be 0, because here we don't, initially it contain 1, so we don't require any reversal operation to make it 1. Now the last index would, the value of here would be 1, because we are, with one reversal operation we are able to make that index 1. Now, for other two, the answer would be -1. Why? Because you can't perform any other reversal such that you can bring 1 here, right? And because you can't do that, the answer is -1. So let's just expand this exact scenario to one more element. Let's say n was 5, right? So there's one more 0, right? And now you can perform one more reversal, right? You can perform this reversal as well. So let's say you perform first reversal. So you make this 0 and you convert this to 1 after the reversal, right? Now let's say you perform another reversal with this subarray. Now after this reversal, you can see this one will come here, right? And this one is coming to a band position. So this reversal is something which is not acceptable. So you can see if you have reversed this, this position would have 1, and the result of this would be 2, because after performing 2 reversal you are able to make this one. But because this reversal itself is not possible because of this band position having 1, we can't perform this reversal, and hence the answer here is still -1, right? So hope the problem statement is clear. Now how to solve this? So there are multiple possible, there are multiple things in the problem. Firstly, we can perform a reversal of size k only. Then there are band indexes as well, right? So let's not worry about band index at all. Let's simplify the problem and say there is no band, there is no concept of band index at all, and we have to solve exact same problem without this band index. So what is the reduced problem? The reduced problem is return the minimum, return this answer array where answer I would denote the minimum number of reversal operation required to to make or to propagate one to that particular index. Now, after like and by performing or by reversing a array of size 4, right? So that's what the reduced problem is now. So let's try to solve that problem first. So this is, let's say, the array, and initially only this position has 1, so that's why it is populated with 0. Now for like for this example, let's say k is 5 and we need to return the answer array. Now, what is the first reversal you can perform? You can see this is the first reversal that we can perform. After performing this reversal, what will happen? This one which was there, so there is one here, right? So this one which is here will go to this particular position, and this position will have one after this reversal. So what does it mean? It means that in one reversal we are able to propagate 1 to position 4. So this would be 1, right? Now, what's next? Let's try to perform another reversal. So what reversal you will do? Let's say you perform this reversal. So if you perform this reversal, the value, the one which was here now will be coming to this position, right? So after this, like basically what you are saying is in two reversal, you are able to propagate one to this particular position 8. Now what's next? You will say before trying this reversal, let's see if any other reversal is possible with one with this particular index 4. Basically, one is at this position now, right? So let's, before even going to 2, let's see if we can propagate 1 to any other index here. So the answer here is yes, you can propagate it. Let's say you perform this reversal. So firstly, we know that this reversal is possible, and with this we are able to propagate this one to this particular position. Now let's say this is another reversal we are trying. With this reversal, if you see, you can propagate this one to this particular index, right? And similarly, this value here would be 2, because with two reversals you are able to propagate one here. Now, is there any other reversal possible with this index? Again, yes. Let's see this particular reversal. If you perform this reversal, the one here would be propagated to this particular index, and the value of this would again be 2. Basically, we are saying that with two reversals only, we are able to propagate one to this particular index, right? Now, we can like you there is no other reversal possible with this particular index. Now you can try this particular reversal with this particular index, or you can try reversal with this particular 2, or you can try reversal with this particular index 8. So if you look closely, what is happening is we initially started with a particular node. From that node we transitioned to some node, right? And from that node we transitioned to some other node, and all these nodes can have one, right? And now what we are saying is we will try one of these nodes, because each of these nodes can now have one. We know that fact, right? So if you look closely, this is becoming a graph, and what we need to find out is the shortest distance from 0 to all the nodes, right? Again, just to reiterate, what we saw that from 0 we are able to uh, traverse to 1 or index 4. Now for index 4, we are able to traverse to index 6, index 8, and index 2, right? Now similarly, if you look again for index 8, you will be able to traverse to index 6, index 10, and index 12, and this index 4 as well. So basically, this entire thing is becoming a graph, and what we need the minimum operation, or the minimum distance from the node 0 to all the nodes of this graph, right? And that minimum operation, minimum distance would give us the minimum operation or minimum reversals required to propagate one from this particular node to that target node, right? So hope this part is clear. Now we need to perform BFS, right? So the code for this would be very simple. We will just start with P. We initially, currently P was 0, but we will start with P, whatever is given, and start the BFS from there. And after the end of the BFS, this array would be exactly what we are asked for. Like this array would be the answer of this particular problem. Now, for performing BFS, what we need to find all the neighbors. So let's now try to find out all the neighbors of a particular node, right? So let's say this is a node I, and we are trying to find all the neighbors of a particular node I. So how to find all the neighbors? So what are neighbors? Neighbors are basically how many transitions you can do, or in other words, how many reversals you can perform that will include this particular index, right? From for all this reversal, you will be getting one particular index into which you can transition to, right? So here, this is like, will you be performing this reversal? First of all, answer is no, because this reversal, if you perform reversal of subarray 2 to 6, this doesn't contain the index I, and because index I is not there, whatever you will do will not affect this particular index. So what we need is from where we can go, from where all we can go starting from index I, right? So we have to include index I. Now how many subarrays are there that includes index I? This is the first subarray, this is second subarray, this is third one, fourth one, fifth one, and the last one, right? So basically there will be exactly k subarrays which would contain index I, right? Now what we don't need all the subarrays, we need the transitions, or in other words, we need the indexes to which we can transition I to. Now if you look closely, this is the first subarray, right? So for this subarray, I would be transitioned to this particular position, right? Now let's try the second one. So this is second subarray. Here you can see I is getting transitioned to this particular index, right? So you can see if you reverse this, I would be coming to this particular position. Let's take the third subarray. In this subarray, I would be transitioned to this index itself. So there is no point in making this swap. So let's take the fourth one. In the fourth one again, I would be transitioning to this particular index, right? And finally, for the fifth subarray, we can see I would be transitioning to this particular index, right? So what exactly are we seeing here? We are seeing that I is getting transitioned to every other index, right? So let's say this is L and this is R. What we are noticing is that I is starting from L, I can transition to L plus 2, L plus 4, L plus 6 up to R, right? Now, is this statement true for every situation? Answer is yes. Now, why the statement is true? Because if you think about it, uh, initially this is your uh, reversal range, and here you say that I is at the last position, so this would be coming to the first position. Now, whenever you shift one thing, you are shifting I by one position. So because you have shifted I by one position, so I is now one position to the left. So exact same distance would be there in the reversed array. So basically, if I is one position from the right, I should be one position from the left as well. So basically, every time we skip one index, we are actually skipping two index for the mapping of I, right? So that's where this statement that if we like all the neighbors will be in the form L to R, where the neighbors would actually be L, L plus 2, L plus 4, L plus 6 up to R, right? So these will be your neighbors. Now, what are the values of L and R? Now we need to find out values of L and R in terms of I. That's what our motive is. Now you can say that, okay, value of L would be the uh, smallest range, or the starting point of the smallest range, or which includes I at the last position. So what would be L? L would simply be I minus k plus 1, right? So in this case, I is 7, and you can see 7 minus 5, which is 2, plus 1, 3. So 3 is the value of L. So L, what we are seeing is L is now equals to I minus k plus 1, right? Now what is R? In the exact same fashion, R would be the last index, right? So let's just take the last range. So in this last range, what is the value of R? R would simply be I plus k minus 1. So the value of R would be I plus k minus 1. So what we just saw, that within this range, we can just start with I minus k plus 1 and keep on incrementing 2 until we hit R, and that would give us all the neighbors for this particular I. Now there are various edge cases here. So let's just remove this from here, right? So there are various edge cases in the form of the last index. So currently L and R, currently there are total 5 subarrays for a particular index I. But what if this index I was this particular index, right? Now how many subarrays will be there? You will see that this would not contain the exact same subarrays. There would not be exactly 5 subarrays for this particular index. So let's look at that. So if you try this is your first subarray, right? Second subarray, third subarray, and fourth subarray. You can't do this subarray because this crosses the array. Like there is no element after this position, so this subarray is not valid. So what we saw, that for the edge elements there will not be exactly 5 subarrays. So here there are 4 subarrays, right? And because of 4 subarrays, R would not be exactly equals to what it was there for the case where we have all the 5 subarrays, right? So now we need to take this into consideration as well while calculating L and R, right? Now what is the general formula for L and R? So what you can say that, okay, uh, how you calculated R? First of all, you calculated R by saying that, okay, what is the rightmost range that I am allowed to take, right? That's how you calculate L and R. So in this case as well, the rightmost range is this range, right? Previously, the rightmost range was this range. That's why the value was I plus k minus 1, right? But now the rightmost range is this range. So the value would differ. And what is that value is something we need to find out. And that would give us a generalized value of R for every scenarios, be it the middle ones or the edge ones, right? So for finding out the value of R, if you remember, uh, we need to first find out the rightmost range. So what is the rightmost range? The rightmost range is, let's say this is R dash of the rightmost range, and this is L dash of the rightmost range. So this we can simply find out because our R dash will collide with n minus 1, and L dash would be R dash minus k plus 1, right? So we know what is L dash and R dash. But what we want to know is the R. And what will be R here? R will be this particular index, because you can see I would be mapped to this particular index at the end in this particular configuration. So I would not, because there is no other configuration, I would not be mapped to other indexes, right? So we need to find out this particular index in terms of L dash and R dash and I. Now, what exactly will this value be? Again, very simple. We know how much distance it is there from L dash. Exact same distance this index would be there from R dash, right? Now, how much distance is there from L dash? It is I minus L dash, right? This is the distance of this particular index from L dash. And similarly, this this index would be at exact same distance from R dash. So basically, you will subtract this exact same thing from R dash. And if you like close, like open the brackets, this would become R dash plus L dash minus I, right? So this is the formula for finding out R, or rather finding out the mapping to which I will belong to for any particular range L dash and R dash, right? So now we just need to figure out what is L dash and R dash for what is the best possible L dash and R dash to figure out the value of L and R. So in this case, the best possible L dash and R dash would be the last range, and similarly for the first one, L dash and R dash would be this. So this would be L dash and this would be R dash. And if you apply the formula, you will see the value of this would come to this particular index, right? So you can see R dash and I are equal, so R dash and I will be cancelled out, and your index would be equals to L dash, right? So basically, this entire thing was just to calculate this L and R, and finally the for like the to find all the neighbors, you will just do L plus 2 L plus 4 all the way up to R, right? So let's look at the pseudo code for this entire thing before jumping to the original problem. So as we just need to do the BFS, so I'm not showing the code for BFS, I'm just showing you the code for uh, this finding out neighbors. Now how we are finding out neighbors, as we discussed, we have to just find out L and R. Once we have L and R, we already know what will be the neighbors. Neighbors would be L plus 2 all the way up to R, right? So this is something we already know about. Now we just need to calculate L and R. Now as we have discussed, L and R would simply mean that what is the smallest value which I can map to and what is the largest value that I can map to. So smallest, let's say I was this, right? So in this case, smallest, sorry, uh, let's say I is this, right? So in this case, smallest value that I can map to is like in the left there is I can map to the smallest index of this particular index. That's it, and that's the large I can map to the largest index of this particular index, right? So we need to find out this L and this R. Now, how we'll find this L and this R? We already know that to this is the smallest range that we already know about, right? This is the smallest range that includes I. So we just need to find out this L dash and R dash for the smallest range. Once we have L dash and R dash, we can simply figure out which index this I will map to, right? So that's what we have done. This best left L is L dash and this best left R is R dash. So what we have done, we find out the best left range. So best left range would be starting from either 0 or I minus k plus 1, right? So whichever is maximum, that would be the starting point of that left range. So that would be the starting point. Now the ending point would simply be this plus k minus 1, right? So once you have figured out this L dash and R dash, we can simply do L dash plus R dash minus I to get the mapping which I will map to after the end of this, like which I will map to for this first range, right? In the same way, we will figure out what is the best possible R. So we find out the best possible right range. So in this case, best possible right range would end at either n minus 1 or I plus k minus 1, right? Whichever is minimum, the range would end at that particular index. And similarly, you will find out what is the L dash and R dash for this range. So R we already know, and L would simply be R minus k plus 1, right? Once you know L dash and R dash, you can simply figure out what is the mapping of I for that range, right? So once we know this L and R, we can simply figure out all the neighbors, right? So just to reiterate the entire solution again, what we have started with the reduced version of the problem where we say that, okay, we don't have a concept of band indexes. We just want to figure out what is the smallest number of swaps required to propagate a one at position P to all other position, right? That's what we need to figure out. Now for that we saw that it is forming a graph. So we initially started at P. From P, we are transitioning to some other index. From that index, there are multiple possible uh, indexes that we can transition to, right? So we saw that it is forming a graph, and we just need to figure out what is the shortest distance from the root node to all the other nodes, right? And that would give us what how many number of reversals are required to propagate the one from the root node to all other nodes, right? So for that BFS, we just need to figure out what are the neighbors. Now we figured out that neighbors is looking like L plus 2, L plus 4, all the way up to R, right? Now we just need to figure out L and R for that. Now what is L? L is the leftmost, L is the mapping of I in the leftmost range, and R is the mapping of I in the rightmost range. So we just do some math for taking care of the edge cases and figured out what is the proper value of L and R. And from that we know what are the neighbors of a particular index I. And once we know all the neighbors, we can simply do usual BFS and figure out the smallest distance from a particular node to all the other nodes, right? So that's what the solution was. Now let's look at the time complexity. First of all, what is the time complexity of this neighbor? The time complexity of neighbor would be order k. Why order k? Because there will be at most k neighbors for a particular node. And why k? Because there are k subarrays. So at most there are k subarrays. So I would be mapped to at most k different elements. So there would be at most k neighbors for a particular node I. And what we are doing, we are just doing BFS, usual BFS. So how many, like what is the time complexity of BFS? BFS time complexity is order V plus E, right? Where V is the number of vertex and E is the number of edges. So in this case, V is N, basically size of the array, and E is N into V, because each vertex or each node has, sorry, N into K. Each node has k edges. So number of edges would be n into k. So this would be the time complexity of your BFS. Now this would not pass the current time complexity because n is up to 10 to the power 5 and k is also up to 10 to the power 5. But we will not optimize it right away. We will look at the optimization later. Let's first try to understand the original problem first. So what was the original problem? Original problem was there are certain band indexes as well, right? So we need to tackle that as well. So let's say there are some band indexes here. So again k is 5, let's say. So what we we can propagate this one to this particular index 4 in one reversal, but let's say like this 4 is blocked, right? Now if this 4 is banned, what it means simply is we will not perform any transition from this particular node. That's it, right? This node is blocked. And if we, how we will take care of this? We can just mark every blocked node as visited in the initial phase itself, right? So what we can simply do, we can simply say that all the band indexes are already visited. Now during BFS, this will ensure that we are not visiting any of the band indexes. And because we are not visiting any of the band indexes, we automatically took care of the fact that uh, we are not populating one at the band index, right? So just to reiterate, what was the condition with band index? Condition in band index was that none of these indexes would ever have one, right? So now what does an edge means? Edge means that from this node you can propagate one to this particular node, right? And edge outside of this node means that once you get one at this node, you will then reach out to these all nodes and propagate one to all these nodes as well, right? Now because this is banned, this operation, that propagating this one to other index, is something which is not possible at all. And that's where we simply marked all of them as visited, so that during BFS, even if we reach here, we will completely ignore it because they are already visited, right? So hope this entire solution makes sense. Now, the entire complexity of the solution is simply order n into k, as we have discussed previously. And this is not sufficient to pass the time complexity of the current problem. But before jumping into optimizing this, let's first look at the code for this particular solution of n into k, right? I would strongly encourage you to pause the video and try to code this n into k solution by yourself. Uh, it's just simple BFS with a tricky uh, neighbor function, and which we have already discussed in depth, right? So this is the code for the BFS, or basically n into k solution. What we are doing is, initially we have a cost array, we initialize it with -1, everything, and we made cost of p as 0, right? And then what we are saying is, we are starting a BFS starting from node p, okay? And we are also marking all the band index as visited in the initial iteration itself, so that we don't visit all these band indexes, right? After that, we are doing simple BFS. We pop one element from the top, and we figured out its left and right. So we already discussed this left and right function in depth. So uh, this is finding out the best possible left and right of the leftmost range. This is finding out the left and right of the rightmost range. And finally, this L and R are the mapping of the I in the leftmost and the rightmost range. Now, what we are doing, simply iterating over everything from L to R and seeing if it is visited, we'll continue. Otherwise, we know cost of I would be cost of top plus 1, and we will visit this node as well, right? So this is the entire solution. Complexity is order n into k, which will not pass, right? Now, we need to reduce the complexity. Now, which of these two factors you can reduce? You can't reduce n because you have to iterate over all the nodes at least once. So this is you can't reduce. So we have to somehow reduce this k, right? Now, what was this k? K was basically uh, the edges from a particular node, right? Now, why this complexity is coming? Because from a particular node, we are visiting the nodes which are already visited, and then simply skipping that part. So basically, this line of the code, if we can remove this line of the code completely, that is, if we know that if we are taking an edge, that edge would lead us to a new node altogether. If that is deterministic, we can simply say that we we don't need to visit this order n into k nodes. We can simply visit order n nodes, right? Again, just to reiterate, what we are just saying is, this order n into k nodes are uh, not are not leading to the individual nodes or the distinct node in each time. It is leading to duplicates nodes, right? So basically, if let's say you start mapping at this node, you will see that, okay, you will map this node to this node, you will map this node to this node, right? So there are multiple duplicates as well. So we have to remove the duplicates, and if we are able to remove the duplicates, then we can say that, okay, we are not visiting like all the n into k nodes, we are just visiting n nodes, because we know that every time we visit a node, we are landing on a unvisited node. And how many times we can do that? Order n times, because there are only n unvisited nodes at the end, right? So that's what the motive is, or the thought process is. So what we need to do is, we need to just remove this line and make some like by doing something such that we know if we are visiting I is already not visited, we don't need to check this and continue, right? Now, how can you do that? Again, why we are like, first of all, why we are doing it? Because we don't have non-visited array, a non-visited index in a particular array, right? That's why we have to iterate over everything and figure out which one is visited and which one is not visited, right? So let's just try to maintain a set of non-visited elements, right? So if we maintain a set of non-visited elements and we iterate over that set instead of this, then we can simply say that okay, we are visiting non-visited elements only. So let's look at the code. The code is exactly similar. So this is the set we are talking about. I maintained two sets, odd and even, because if you looked at above, we need to iterate over a set, right? So let's say set contains 1, 2, 3, 4, 5, 6, right? Now, what are the neighbors? Neighbors are the mm, alternate elements, right? So neighbors, if L is 2, the next neighbor would be 4, next neighbor would be 6, and so on and so forth. So basically, neighbors are either all even or all odd, right? So that's where I maintained two sets, odd and even, right? And in odd, I put every odd elements, and in even I put every even element. I skipped uh, P because P is already visited, right? And similarly, I skipped all the band indexes. So previously, what we were doing, we were marking this using this is visited array, but now we will be using this odd and even set. So we just marked, uh, we just removed all the band indexes from this odd and even positions. Now once we figured out L and R, we'll just see what is L. If L is odd, then it means that we just need to iterate over some of the elements of this odd set. And if L is even, it means that we just need to iterate over some of the even elements, right? So let's look at one of them. So if L is odd, what we are saying is we will iterate over everything in range L and R. So we just figured out the lower bound of L, and we are incrementing it until we hit R, right? And for each of these nodes, we know that all of these nodes are not visited at all because we are only maintaining non-visited elements here. So each of these nodes are not visited. So we can simply uh, like skip this is visited check completely and simply do these operations. So what we are doing, we are uh, like we are populating the cost and we are also pushing that particular index to the queue, and finally we have to erase this index as well, because what we are maintaining is we are maintaining all the non-visited indexes, and because we have visited all these indexes in current iteration, we have to erase them as well. So that's what we are doing. We are pushing it to a vector and finally removing it altogether at the end. Now notice that you can't simply put this line here, because if you put this here, the iterators would be changed because you just removed the odd, you just remove this particular IT. So iterator would be changed, and this would not lead to, like IT plus one would not lead to you to the next to your correct next element. So that's where we are not erasing anything. We are not modifying the data structure while we are reading it. We are modifying it at the end, right? So this is what we have done for odd indexes, and similar thing for even indexes. We are doing exact same thing on even set, and also populating the cost and pushing to the queue, and finally removing it from the uh, set because we have visited all of these indexes in the current iterations, right? So now if you look at it, what we are doing in each iteration, we know that we are only visiting edges that are not yet visited. Hence, we ensure that we will be visiting at most n edges or order n edges, right? And because edges are something that we are using set to maintain, so every time we access an element from this set, we would be requiring logn time. So the complexity would now become order n logn. So we reduce the complexity from n into k to order n logn, and that would pass the time complexity of the given problem. So this code is something I have submitted it and verified it as well. So hope you got the solution. If you have any doubts in this particular problem, please post them in the comment section below. I will be happy to answer. If you like the video, give it a thumbs up and do subscribe if you're not already. And I will see you in the next one. Thank you.